thank you all for showing up. It is my great pleasure to introduce Alex to all of you. Alex is he until recently was a master's student at EPFL, but he just defended a couple months ago, and he's no longer at EPFL. I hear you're going to Anthropic next, which is exciting. Alex's master's thesis, even though he was at EPFL, he was actually visiting as part of my group, and we worked on this project together, sort of his work or his master's work that he's going to be presenting today. This is a little different than the other talks we've seen because this is not yet published. We're in fact rushing right now, sort of in the midst of an OSDI submission. We hope we'll make it in time. And the main purpose why we're doing this talk today is because we really want to get feedback from you about what things might be confusing, if some things appear more interesting than others, things like that, so that we can incorporate your feedback into how we sort of formulate things and write the OSDI paper. Okay, so without further ado, I'll hand it over to Alex, please.
Thank you, Kenan, for the introduction. Hello, everyone. It's my great pleasure to be here. And today we're going to be talking about how can we design better tools for developers to define and enforce privacy guarantees in distributed applications. Okay, let's go. So when developing applications, developers actually have to comply with data use policies of different kinds. One of the most known is regulations, such as GDPR or HIPAA. But there's also security policies such as access control that monitor resources access and whatnot. And otherwise, there's going to be terms of services, or let's say on the broader term would be privacy guarantees that are proposed by companies and by the products they offer. Now, when developing applications, developers have this cognitive load of having to manually enforce these policies, and it becomes kind of tedious to have to enforce them manually. And to that effect, there have been some, and sometimes mistakes can happen, privacy bugs can happen, which end up being costly and disrupt the application flow. Now, to help developers not run into these mistakes, there have been some privacy enforcement tools that have helped. Now, one of the issues that we run into is that these privacy enforcement tools generally fail to be compelling when writing distributed applications. Developers are usually isolated when having to think about code, and there's like a whole organization mess about enforcing end-to-end guarantees. We argue. Apologies. So modern applications are usually built with microservices. Let's take an example of an e-commerce platform that is made with multiple services that showcases the problem we run into. So we have a front-end service that is exposed to the client, to the end client, the HTTP client. And in the backend, we have a checkout service that orchestrates the whole checkout process. And for example, we have a shipping service that sends the orders and a payment service that is responsible for handling the credit card information, sending it to the third-party processor. Now, one of the issues here is that even if the front-end service developers, for example, try to reason properly about privacy and define properly their privacy considerations, there is no way for them to know whether or not the checkout service or the payment service developers also abide by the same properties. We argue that it should be easy and ergonomic for developers to define and enforce privacy guarantees in distributed applications. Now, let us look at perhaps what is the threat model that we're talking about here, and what are we consider, like what will we be talking about? On the broader scope, we try to think about organizations as being safe. The processes are well defined. Companies have no incentive to be truly malicious. They have products that have privacy that have privacy agreements, terms of services, and also regulations. So we consider the organizations to be trusted. That also means that some people within the organizations also have to be trusted, such as root level users, OS developers, the OS in general, also the hardware. And we will also not be tackling the side channels here. On the other hand, what we want to discuss is how to properly handle and confine, of sorts, developers that actually write the application code that we do not trust. Developers can be either incompetent because privacy is hard to reason about, or even if they try to be somewhat malicious, Tahini also protects against that.
Sorry. The developers write the software that you trust. So in one sense, you trust the software, but not the developers?
So you trust the software stack below the application, which is going to be like OS, the containers, hardware, firmware.
Okay.
You trust everything except
the application software that is specific to this deployment.
Mm-hmm, mm-hmm. So let us look first at what is the motivation behind creating this new system, right? Why is Tahini important here, and how the existing work has some evident, obvious shortcomings. So historically, we have been trying to tackle distributed privacy policies using distributed IFC that uses some security labels that is a lattice of security labels, kind of opaque. I mean, you can look at what it looks like. This is taken from like the seminal paper of the IFC. And most importantly, distributed IFC policies focus on inter-process interactions. It's very hard to reason about the data flow within a program if all you think about is how information flows from one program to the other. What that means in practice is that if you want to have end-to-end guarantees, you need to have some local variants of the property of policy enforcement, and then you have this distributed business. So, for example, here, using again our example with the e-commerce platform, let's say, for example, the front-end service and the checkout service have no reasons to use the data of the user. They just forward it, for example, to the payment service. And as such, they can be qualified as having a high security label. Like they do not need access to the data. They can have some strong label, like some strong privacy properties. But obviously, the payment service needs access to the data. And so now we have this sort of weird business because the lattice only flows in one direction, where we have declassification. And in practice, what happens is that you just strip away all the guarantees. Kind of confusing. I know this is exactly the issue with distributed IFC. Now, there have been some other distributed privacy mechanisms and tools, systems that have been developed. One of them being Rioen, that basically encapsulates all the services and all the modules within SGX, but is pretty harsh as there is no declassification allowed to happen. So you are confined within an SGX and Rioen ecosystem. And also running everything in SGX is pretty slow.
If you're trusting the runtime anyway, then why do you need enclaves?
That paper's threat model is different. That paper's threat model is kind of the same problem, but in a much more paranoid threat model where you're not even trusting the cloud provider. So it's not entirely apples to apples, although they're trying to do the same
thing. On the other hand, another system called Riverbed tries to generalize this, the privacy properties and whatnot. Like you can just plug your service, have the privacy properties be enforced, but they have this weird issue where an application, user data with a policy can go to different universes depending on the policy they have, which in practice is very fragments the applications. So, for example, social media. It means that if your data has some policy and you try to talk with someone else with a different policy, you can't because you're split into different universes. So this is obviously very practical also for application development and for a lot of modern applications. Now, there have been some recent advances on better systems for local policy enforcement. One of them being Carapace, that basically tries to reuse IFC and distributed IFC, but in a more ergonomic way. There has been Rulekeeper that's tries to do that for JavaScript, but it's kind of unsound. And there has been more recently Sesame, made by our good friend Kenan, that tries to, is a hybrid method that tries to enforce also privacy guarantees structurally, like secure by design privacy compliance. So we argue, after seeing the scope and the existing work, that developers actually lack practical tools to enforce end-to-end policies in distributed applications. To that effect, we have built Tahini that tries to provide those guarantees. And the way it does so is by taking local enforcement policies, extending them beyond, allowing flexibility of policies, and then verifying that the privacy policies are actually enforced. So let us look first at the setup. Imagine you have two services communicating, such as the front end and the checkout, that each have some local policy enforcement mechanism enabled. And in the base case, without Tahini, you would have, if you want to have distributed privacy properties, you would have a system for local policy enforcement, and then a system to basically patch the two together. Otherwise, you lose at the end-to-end guarantees. This interaction between the two services is the critical part. It's like, how do you ensure that guarantees on one end is also enforced on the other end? And is also enforced on the other end. And so to that effect, what we will do is we will base ourselves on a reference local policy enforcement mechanism, namely Sesame, that I will quickly explain so you have the relevant information here. So what Sesame does is it takes a sensitive piece of data and binds to it some fine-grained policy. Throughout the application, the data flows with this policy being attached everywhere. And what the policy specifies is disclosure conditions and combination conditions between data, and if ever you want to access the data, under which purposes can you actually access the data. Now, this is not sufficient in itself. So there's also some static analysis that helps to enforce those properties. We will get around to talk about it a bit some more. But there's also obviously, that is very important, some escape hatches, because sometimes you need to send the data to some unprotected service, or like you need to send an email. And to that effect, Sesame ends up relying on code review and signatures from trusted developers. Not the application developers, from some trusted developers, which I think is important to specify. Now, what Tahini does is that it takes the picture we had previously with the two separate services that each had a local policy reasoning and unifies it. How does that look like actually in practice? So what Tahini does is that it has some interface that provides safe RPC clients and server. When trying to communicate between services, the front-end service is going to have the data that is being policied, within the application, and then at the process boundary, the data and the policy are going to be sent over the wire to the other service that then get recombined and attached Sesame style by Tahini. Obviously, for the application, this segmentation of this is simply serialization and sending over the data and the policy over the wire, right? But this is hidden away from the application. It's transparent to the application so as to ensure that only Tahini can manipulate the unprotected data. What that provides eventually is that application never, I need to emphasize this, application never see the unprotected data whatsoever. Only Tahini is allowed to manipulate that data. Now, let us look a bit more at how can we, provide better service architectures and how can we provide better policy configurations. So let us take an example here, where you have the front-end service that says basically, I don't need to access the credit card of the user. So my disclosure conditions about the data is, I will reveal the data only if I send it back to the client. I don't need to access it whatsoever in my internals. I can forward it as it is being protected, but the disclosure itself of the data is only going to happen to the client. Sure.
Can you do something like save it in the database?
No. That would need to be specified in the policy, and the user would have to, we'll get around to it, but this would need to be specified in the policy. If you want to save it to the database, this needs to be specified in the policy.
I feel like that's a rushed answer a little bit. What do you mean?
I mean, it's held in memory, and maybe it would be stored, persisted, encrypted. How do you define the different things that can happen to a bunch of bytes?
Right.
Some of these are legit, some are not.
Yeah, good. So this is let me answer that question because it's about Sesame. This is like a lower level question.
Yeah.
The bytes in your memory, you sort of never really have. So this is all based on some sort of type system that we developed on top of Rust. And the idea is that the application cannot access the bytes directly. The bytes are sort of protected in some location of memory that is outside the range of the application. And the application has handles to it. And so you have basically a kind of a pointer to the data, but you can't actually deref them. Think of it that way. And so you can pass this around, you can call functions, you can put it in vectors, get it out of vectors, things like that. The moment you want to do something that involves the bytes, then you have to use some of these techniques that we have in Sesame. One of them is based on static analysis, which is Alex hinted at a little bit. If you want to say like add two numbers together, we can statically verify this operation is okay, and then you do. If what you want to do is take those bytes and put them somewhere else, extract them out of the protection boundary, write them to a database, for example, or send them over the network, then what happens is you have to go through Sesame. Sesame executes a policy check, and then the policy check has information about the context, about who's the logged-in user, what is the purpose of this operation, where are you trying to write it? Right? That context is trusted, is provided by Sesame. The policy check looks at it and decides, yes, this is allowed, or no, that's not allowed. So a write to a database would be one such example. And if you're trying to write the database, it would be basically the policy check would be asking itself questions like, should this data be written in the database? Is that allowed? Is it encrypted first? Stuff like that. Who's writing a database for purpose? So that's how it's done. Thanks.
So these checks happen at compile time, right?
No, so there's most of the stuff happens at compile time. So like you're trying to add numbers together, and we can verify statically that you're okay. These things happen at runtime. These checks that are the second type of checks, because the context information is dynamic. So for example, these are things like maybe you get to maybe this is some sort of let's use this credit card example, right? Maybe you as a user, you're saying, I'm okay with my credit card being saved to the database. Like you check that box, and you've seen this on online stores a lot where you say, store my card for future use. Say you check it, right? The fact that you checked it now means that your card can be written to the database. And so the policy check needs to know, right? If you don't check it, then your card should not be written to the database. And if the application tries to write it, the policy check will fail. But that information is only known at runtime. So that check has to happen. That last check has to happen at runtime.
Thank you. All right. So using a simple example here of policies, the front-end service considers that its only purpose about the credit card is to forward it to some later service that will manipulate it or return it to the client as is. So let's say, for example, that now the checkout service also realizes that the checkout service developers realize that they have no incentive to use the credit card, and they use the same policy. They're like, okay, sure. Now, on the other hand, the payment service, well, they have some business purpose about using the credit card. They need to reveal it to some third-party processor. And obviously, we can safely assume that a third-party payment processor is not going to be using Tahini. Like, we do not want to make strong assumptions here. So there is going to be some disclosure and some unprotection. Well, we have a mismatch, right? Because now we have this policy on one end that is somewhat safe, pretty safe. And then we have this less safe policy. And how do we bridge the two, right? Because the policy is being forwarded with the data, how do we actually bridge? We do not want developers to be able to simply modify the policy in an unprotected manner. So one solution here, that is a non-solution, is to simply ask the front-end service and the checkout service to also use the payment service policy. So now the front-end and the checkout service developers, they're like, hey, okay, I can also reveal the policy. I agree to also reveal the data if I need to contact a third-party processor. Now, that's a non-solution for two reasons. One, it can reveal service internals. So let's say now that there's also, I don't know, a recurring billing method. So now this is also leaked in the policy. And then there's also some leakage surface that is being involved, right? We want to minimize the lines of code that can wrongfully use the data. So there's no reason here to basically have looser policies where we don't need to. So what do we propose? We introduce a new mechanism that is a policy transformation. So here is like some code snippet. I have the credit card policy, that is the strong version, right? That says only reveal to the clients. And I want to be able to transform it into some payment processor policy that says, well, you're also allowed to reveal it to the payment processor. Okay. Now this code should not be able to be invoked in application code naturally I hope you understand the reason. I will still specify them. Otherwise, some developer can just downgrade the security properties at any time. We need to make sure that transformations are safely invoked. So how does that happen? A transformation is being provided a context that, well, I guess I'm providing to immediately. It's being provided a context by Tahini that specifies where is this transformation invoked. The context specifies the service and the method that is being used in this current transformation. And We can trust the context because it is being provided, again, by Tahini, in this safe interface that I provided earlier. And developers specify under which services and which methods do they allow this transformation to happen. And they also define the exact transformation semantics. Now, I keep saying developers, define blah, blah, blah. This is trusted code, right? This is transformation code. This is not written by application developers. This is written by, again, the trusted developers that will sign the Sesame escape hatches that will, be responsible for defining the policy code. Loosely in Sesame, they're called policy engineers. We reuse this term and extend it to also include some, very hard-thinking developers that try to make sure that all the privacy properties are properly upheld and whatnot. So in our case, you have this very strong policy, and it ends up being like transformed into a policy that you're allowed to send the data to Stripe or PayPal. Great. We have now enabled services to transform from one strong policy to a weaker policy and ensure that it is safe. Now, this is basically all during development, and it's like a combination of localized properties, right? How do you unify everything? And to that effect, we provide or force developers to actually audit and verify the privacy guarantees of a service they will try to connect. Let's look at a bit what were, again, the setup and what does that look like. So again, the front-end service can, reason strongly about privacy properties, but they have no way of knowing whether or not those properties are upheld end-to-end. And what exactly is the policy of the payment service? What happens in the backend? There's no way to know about that. So how does the front-end service know that the payment service is actually doing the good thing with the data and is not, having some very weak policy that allows it, I don't know, to print to file, or to do whatever. So one non-solution is to simply say, well, I don't know what you're doing. I don't have visibility into what you're doing. I will trust that you're doing the good thing, but there's no way for me to know that. That's not a solution. The other one that is, kind of historically the way people verify these properties is you do an audit of the code base. While you don't want to have to audit all the business logic, you don't want to have, the cognitive load of all of that. You want to have some constrained audits about only privacy critical information. So how do we do that? To enable this property, we use a technique that is trusted compilation. Now, there are many services, many systems there are a couple systems that enable trusted compilation. Usually it's like you have your build toolchain that is being run inside some TE and you can attest to it, okay? But specifically for us, we will look at what is happening here. And you take as input a source code, somewhere along the compilation, you have this Rust intermediate representation, and we run some static analysis toolchain that is the Sesame toolchain and some additional toolchain that we use for Tahini specific purposes. That would be, you need to extract the policy to know what policies are being used in the specific service. You extract the transformations to know, what is happening, what are you transforming into, what are you transforming from. And then also all the escape hatches, these critical regions that, declassify the data, you also need to be able to monitor them. We produce two outputs. There's the ELF binary that is the output of a normal compilation. And then there's a trusted binary, certificate for the binary that will be signed by some trusted key source. And what that looks like, what that looks like is basically this. We just have now some file, some certificate that specifies to me, this is a summary of some sort of manifest about privacy configuration of a service that specifies to me all the privacy properties of a service. Now there's a lot of stuff here. We have the service name and some other information. What are the policies being used? Do I implement locally some policies? Do I import from upstream some other policies? How do I use them? The critical regions, which are the escape hatches. If I end up connecting to some, I need maybe to this slide. Sorry. We have all the policy configuration, and then there's this additional stuff that is very important to Tahini, which is if I, as a service, I am connecting to another service down the road, well, I want to be able to inform my client about what are the privacy properties of the service I'm connecting into. And to that effect, we also include recursively all the downstream services, all the manifest of the downstream services. And eventually, because this happens during compilation, we bind this manifest to a specific binary hash that ensures that the privacy properties are only valid for a specific build. Now, because we have only the static business, there is a chance that, at runtime, the privacy configuration could be different from whatever clients review. Could be different from whatever is the output of the choice of compilations, and then client actually get to audit. So what does that look like in practice? The property we want to uphold is that the runtime guarantees are actually the ones that have been approved, statically ahead of time. And to that effect, we have some lightweight attestation mechanism that allows us to verify this. Now, we introduce a sidecar, a component that is trusted, that is very minimal. In effect, what it does, it receives a binary, hashes it, stores some information about it, and then starts the process. What we do here in our attestation mechanism is we have the sidecar, receive this binary, measure it, launch it onto the host platform. Now, down the road, maybe the client wants to use the service, and before connecting to the service to verify that the privacy properties are upheld, it will first, verify that the sidecar is some trusted component. The trusted component is actually running, and we can actually trust its output, and then it will try to ask for it about service information. It'll be, hey, sidecar, I want to connect to, the checkout service. Can you tell me what is the running binary and what is its privacy configuration? The sidecar obliges and responds with this information. Now, the client then decides locally if whatever is being provided by the sidecar actually matches what they want. Is it one of the privacy configurations they have validated beforehand? If such is the case, they will connect to the service. Okay, great. Now, there's an important thing happening here, something important that is missing, namely, between the time the client connects to the sidecar, requests the information and connects, and then the client connects to the service, well, the service could be hot swapped, could be rebuilt, could be redeployed. And so we want to have some additional guarantees that basically bind this whole stuff together. And so now when launching the process, the sidecar is also providing some secrets to the service. And then when the client connects to the sidecar, it also retrieves some public part of the secret, and the secret is then being verified during connection establishment. Using so, we have, this attestation mechanism enables us now to, go from something that is being statically approved and is somewhat minimal, all the way up to runtime guarantees without having some TE or some heavyweight mechanisms on the critical path of the data. This only happens at connection establishment. And I think it's important to emphasize that. This is an attestation mechanism that only happens at connection establishment, and the critical path is clear of all machinery, right? This is some regular TLS connection that is going to happen during the phase 6. Now, one of the good perks about this system is that because we only look at basically what is happening in terms of privacy configuration, if you rebuild your binary and it ends up that you don't change the privacy configuration, it just has a different binary hash because you do some business logic change and whatnot, well, Tahini can automatically vet your new manifest, and it fastens the process and then it fastens the process and reduces the burden. Yeah.
In the previous slide, how do you make sure that what the client has attested in the T is indeed what the service is running?
So repeat the question. We couldn't hear it.
Sorry, yeah, I was asking how can we ensure that so there is an attestation process in the, let's say, first 4 steps, but then the client connects directly to a service that is not running inside the TE, right?
Yes.
So how do we make the connection between what the client has attested with the TE and the actual service that is running on the server?
So the sidecar is a lightweight component that which is very easy to like minimal to audit, and so it's like you know the hash of it's in its entirety, and the threat model of Tahini is that we trust the OS, and so we trust also the control path that allows the sidecar within a TE to launch a process on the host platform.
Okay.
Yeah.
And then there's one more piece, which is that the sidecar gives the service a secret. Think of it as like a share of a key exchange. In reality, we're using TLS delegated credentials, but you can think of it as a certificate. So it gives us the service, and then it gives the public part of it to the clients. So when the client is connecting the service, it knows what to expect.
Yeah.
And if it connects to something else, it wouldn't have the secret. The handshake would fail.
So let us look a bit at the evaluation and how we have used Tahini for some sample applications. So we have some lightweight application that basically has a front-end service that orchestrates serving some LLM to the client, stores the information, has some user accounts info details, and also serves ads to the user based on the LLM conversation. So let us try to engineer what policies could look like in that specific service, specific application. So there are like 3 grand sets of policies. There's the access control policy that ensures that whenever you pull data from the database, like to store data in the database, this is like properly stored from the user. Then there's like simply an on-off switch that allows you to have ephemeral conversations that ensures the data is not being stored in the database altogether. And then there's some advertisement properties and policies, such as do you agree to ads? Do you agree to targeted ads? What processors do you allow for the ads? Now, so this would be the policy schema kind of. The front-end service, would communicate with the LLM provider and the database using some set of policies. And the advertisement policy, the advertisement service would use a different set of policies that is advertisement specific. Let us look at one end-to-end application flow, using this basically conversation/chat endpoint. So the user sends some conversation to the front end. The LLM service provider processes this conversation, infers, generates some tokens, and then the front end, if allowed, stores the user conversation in the database, and then tries to retrieve ads for that specific message. We evaluate Tahini end-to-end, so from the client viewpoint, and we measure end-to-end latency. We want to ensure that we wanted to encapsulate everything that is relevant to Tahini, namely policy transformation, policy checks, serialization of policies, and we have some reasonable numbers. The unmodified application, is running in 4.3 milliseconds for the end-to-end endpoint. And we have 494 for the application using Tahini, which in itself ends up being about 40% overhead on the median and 30% on the P95. We are actively looking into reducing those numbers. This is our area of improvement. Now, one great thing also that is relevant about Tahini is how do we focus the developer effort. This is like the initial selling point is we want to reduce the amount of code that needs to be audited. And so we, using this LLM application, we measured that the unmodified application is about 2,000 lines of code, and basically only 350 of them that have been added from the application are critical for privacy. Had not Tahini been there, we would have had to audit all the application code, which, this is some very small application. You can imagine how much more the business logic grows compared to privacy code. We also use Tahini for some bigger application that I won't detail further, not too much further here. It's called Online Boutique, Hipster Shop. It's like some Google benchmark application that uses like 11 or 12 services that tries to serve this e-commerce platform. And, you can see that there's a complex mesh of policies. There's a lot of the front end is like connected to all these services at once. You need to have some flexibility in the policies. This has been very, very instrumental to learning how to properly design and be ergonomic on the transformations, particularly. One such example of policies that we use in that case has been what I've been showing throughout this presentation with the front-end service, the checkout service, and the payment service that basically says, do not store to database, do not reveal, do not reveal, do not reveal. And then, eventually the payment service has to use this property to be able to send it to pay. So Tahini is, we consider it to be some sort of stepping stone into other areas of usage. One of them being, well, I guess I was saying that. One of them being, maybe we can attest to supply chains. Maybe you have some dependency that you want to be able to attest at runtime. We consider this to be a very interesting use of Tahini's attestation protocol with the trusted compilation, the manifest. Also, we would like maybe to make Tahini a bit more flexible and independent, not so bound to Sesame as a local policy enforcement. In principle, Tahini is independent from the local policy enforcement mechanism. And then we are running into a bit more issues with the ergonomics regarding how do you handle this recursive manifest disclosure when you have complex nested code checks. In conclusion, Tahini helps developers extend their properties. They think locally about how their service can enforce some properties, and we have automatic extension of those properties in the distributed applications. If the needs arises, Tahini allows for flexible service policy configurations, architectures, and without breaking the properties. Additionally, service clients can easily know what other guarantees are being upheld, and those guarantees are ahead of time. There's no runtime overhead on that end, and Tahini ensures that this is enforced. Ultimately, the overhead are reasonable. Thank you very much for your attention. I will be taking any question if you guys have any.
We also have questions for you because we'll see. I think one thing that came up when we were talking earlier, you asked about it, is sort of the threat model. And I guess, is the threat model clear? And if so, is it convincing?
Can you go back to the answer at the threat model?
Yeah, let's go back to the threat model.
Yeah.
Essentially, you're saying that you are supporting everything that is not application specific, including the off-the-shelf operating system, runtimes, and so forth, as well as Tahini itself, which again is not application specific. You're furthermore trusting the policy specifications.
Yeah.
But you're not trusting any of the code written by the application developers.
Yeah.
I think that could be maybe better conveyed, but it's a reasonable model.
The idea is the organization, to an extent, we believe is incentivized to try to do the right thing because they want to avoid fines or they want to avoid breaking the law, whatever. Our realization of that is to say we're thinking of the organization as being split. There's call them root users sometimes we call them policy engineers. We should choose one of the words and say it consistently. But think of it as like privileged developers versus regular developers. And like in a big company, you might have like hundreds of developers, but only a handful of privileged. Privileged developers are responsible for writing these policies down. Because the policies at the end of the day, these are the specs. So if the policies are wrong, well, we can't give you any meaningful guarantees because the policies that we use. Those parts are trusted. They have root access to the machine, they can influence the hardware, the OS, whatever, that entire thing is. But then the sort of the army of developers that you have in your organization, which could also be just like LLMs writing code at this point, really, which can be incompetent or they can be spies, or be whatever you want it to be. Those we are actively protecting.
Well, if they really are misbehaving, what prevents them from executing a shell command that would run a different binary that would just exfiltrate everything?
So good, very good question. So trying to make clients or the client and an RPC connection connect to a different server, to like a different binary, that wouldn't work because of that attestation protocol. They would need somehow to get the secret out of the binary and inject it into their modified big binary.
But another binary running under the same user on a Unix machine can just ptrace or
so that's the point here. Is goes back to this idea of the trust domain. They need to be running. They need to have this binary running in the same trust domain. So they basically, in our view, it's kind of like saying they need to have organization level access as opposed to guest access.
Well, I mean, in a concrete instantiation on a typical, say, Linux installation, all binaries running under the same user can peek into each other's memory space.
No, I agree. But okay, we wrote some application together. Let's say I'm the trusted user in the I'm the trusted developer in the organization, call it the policy engineer or the user. I have my own account on the server, right? I will run that application under my account. Now you might have access to the server in a limited way. You have your own accounts. You can run some other binaries, sort of independent thing from me to you have some limited access. You will not be able to exfiltrate secrets from my user because you are different.
Sure, but think about the say the front-end software. Mm-hmm. It's meant to be constrained, right? It only has a handle to the credit card and it can't access it, but it can execute another binary which was not compiled with all the guarantees, and that binary can look back into its memory and exfiltrate the credit card.
Okay, I think I understand what you're trying to say here. It's not that the malicious developers are themselves logging in and executing a bad binary, because if they did, they would be using a different Linux user, and that would work. Okay. You're saying they write some malicious code that somehow finds a way to invoke some other thing and have the other thing look into them. Okay. So this, I think, boils down to the local sort of threat model that we inherit from Sesame, where in order for them to do this, they don't have this capability. It's sort of restricted by design from Sesame. So in order for them to do this, they need to use one of these escape hashes. They need to use a critical region. And every critical region has to be manually reviewed and signed by one of the authorized developers.
So the point is that running an exec call is not an explicit escape hatch for the secret data.
I agree that, okay, if you're thinking, okay, so you're thinking about them, somehow they get some other binary on there, they exec it. Okay, interesting. I'm going to keep that in mind. We'll have to think about that. If it's something that is happening within the binary itself, I'm fairly confident that the protections that we have is enough. You're describing something where I found some way of putting some bad binary on the server, and then I exec it somehow from what I wrote. Okay, good.
And all you need is shell commands and the typical unit.
Yeah, but it
doesn't really require bad binary.
You need to be able to exec, which I think we could turn off that ability for you and make exec into one of these critical regions as well. I wonder how common this exec thing is, but we have to think about it. It's a good point.
And this generalizes, right? You would have to think about any indirect way you may have to basically.
We've thought about a lot of these indirect ways. This exact one we haven't thought about. The one other category of indirect ways that could work as an attack is side channels, and that we don't protect against. That's outside of us.
Yeah. So basically, you're in the same game here as trying to defend against escalation out of a compromised server process. Right? Imagine you're running an Apache server and someone sent a bad request. He's now controlling your Apache instance, but you want to make sure that they can't do anything else, and in particular, they can't exec shell commands or change system configuration files. Change tilde/.ch, which is equivalent to exec. And right, all the literature about how to contain HTTPD also applies to how to contain a Sesame binary.
Yes. In fact, I would argue it's probably easier for a Sesame binary because this is all in Rust. And so the language is a lot easier for us to sort of constrain both dynamically and static.
Can you go forward a slide or two? I don't remember which one it was. There was one that.
What about
that one? Can you go to the point where you have the high, I think the high, low? confusion I had when I saw that, and I guess I still have it, is you're saying that the privacy schema is high on front end and checkout and low in payment, but at least historically, in order to be allowed to be a payment service, the kind of policy that you have to get approved for would tend to be high. So it made me question whether I understand what you mean when you say high, and low.
I agree with you here. It's not so much, I guess the definition was kind of informal in that sense. I'm not properly using the labels here. High refers mostly to like, what are the levels of protection? You don't need access to the data, there's going to be a high level of protection on the service.
Oh, so it's about the protection.
Yeah, but
This is the label attached to the data, not the privilege of the services.
So by low, it means you need more of the information because
you need more access, so you have lower protections being enabled.
Got it. Thank you.
And this part is actually quite a real problem. Even it used to be a real problem, even ignoring distributed systems. Just with IFC, one of the sort of pain point. I mean, there's a lot of pain points with IFC, but one of the big ones is that you often would need to do something that the policy will not allow you to do because the policy is written in a really strict way. But you still need to do it nonetheless because that's actually the point of your application, which is why IFC systems have declassification. But I think that part of the vision here is that this idea of a declassification, especially in a distributed setting, is something where you can really shoot yourself in the foot really easy. Because if you're a developer of some microservice 5 steps down the line, and you have the ability to just say, I want to declassify, now you can do whatever you want to the data, I don't know. And so we want to have, rather than this sort of unrestricted declassification, think of it as a more scoped down, restricted declassification. We don't call it that, we call it a transfer. It's kind of a much more limited thing that gets exposed all the way up to the code, so you know about it.
So you discuss this in the context of services, microservices. How much of this ports over to, say, a mobile device with different applications and services and APIs and Android activities, where you may say the front end, the UI activity is not supposed to leak the credit card number that it got, it's only supposed to forward it to the payment service.
Yeah, I think a lot of this could extend there. The two main things that we would need to think about them is, well, the first one is the attestation part of this. It is not entirely clear to me how you can do it, but perhaps you don't need it there because it's all part of the same document. So perhaps that's not super important. The other thing is a lot of what's being described here, there's not a lot, some of the details we've skipped over, it is very Rust specific. And so to try to apply this to another language, you would need some sort of proper framework of what we call local enforcement, the thing that happens within the activity that we can then build on and extend to an intra-activity, thing. Some of these systems do exist in Java, but none of them, like, I mean, you have GIF with one, that's GIF, or some of these things exist, but I don't think they're quite as easy to use or as practical as Sesame or some of the other related work that you mentioned, which is all Rust, well, not Woolkeeper, but the other ones are all Rust-based. So I think that would be really the pain point.
Mm-hmm.
But in principle, what we're doing with Tahini is independent from the medium of inter-process communication, right? We're using RPC here as an example because we want to use web applications. This is also like the baseline for Sesame's use case, right?
But it could be Android intents instead of RPC.
Yeah, it could be anything. Yeah, one of these things that could be interesting for the future is this idea of maybe using this for supply chain attacks, where you can think of it as either you're not worried about the supply chain of remote services, but you could also think of it as every single library, every single dependency is like its own little service in this sense, and you get the same kind of behavior when you're passing data with like a function call. That would be kind of in the vein of what the activity.
The attestation mechanism, I guess, we use it in the context of Tahini, but in practice, you can verify any static property about the binary.
Another question. Can policies reason about downstream policies? For example, can they say, I'm willing to give this credit card to anyone as long as their policy ensures recursively that the credit card only ends up with a specific payment processor? Yeah. So for example, I can give my credit card to a database as long as I know that the database will be respecting my preferences in the future.
Yeah, we can do that. This is part of the transformation API that we have. There's this notion of a context, and you get to superimpose more information in this context. So what you're describing is exactly what we want to do. It's exactly what we support.
But so I guess this is half the answer. The other half would be what you're saying is basically I as a client connect to multiple, like there are services down the line. Sometimes at some point I lose track of the data, and I want to know that when it is being used down the road, it will enforce this policy.
Yes, I'm no longer there, but I want to know that the policy I'm handing it to has certain purposes.
Yes. So the way you could think about it is at some point there's going to be a need for this information about I want my data to be used. There's going to be some context that needs to be stored with the data in the database. Tahini is not so much worried about the storage layer. There are some other projects that handle this, but you can assume that if you want this preference to be stored, it will be basically part of some policy states, right? The policies are dynamically configurable. They can hold states. So there's going to be at some point a state that says, well, down the road, I want you to only use this with a specific payment processor. And now when I connect as a client, when I have this running session, I have all the manifests that tell me whether or not this state is properly being stored and will remain attached to my data down the road.
So it's a bit of an inductive way of thinking where we secure one hop at a time, right? But because every hop is sort of secured based on the previous hop, it ends up being just inductively, it works regardless of how deep, how many layers down the road this transformation that you were developing. And I guess the real point is this transformation business that Alex was talking about. You get to say, I don't want this to be transformed at all. Like nobody's allowed to transform this policy ever, and then everybody's stuck. They have to use that policy. Or you get to say they're allowed to transform, given that they meet this predicate encoded in some sort of function, and then that gets involved one hop at a time, one hop at a time, one hop. It builds inductively into like a chain of whatever.
How is the function encoded? The one that needs to be passed down the road?
Could you go to the slide that just mentioned? Yeah. It's not the greatest example of this, but I think it. Right, so something like this thing, the policy into this is like a trait that we're defining. You're saying as the CC developer, you're saying, I'm allowing the CC policy to be transformed into a payment processor policy. I don't allow it to be, if this is the only code that you wrote, this is the only transformation you allow in your CC policy. Okay? You could do this a bit more generically. There's, you could do some sort of Rust shenanigans where you're saying, I allow you to transform to any policy type P as long as some trade.
And this can be conveyed.
This is conveyed with the whole attestation thing, one hop at a time.
I think there's a type which would be an or rather than an in.
Probably right. Yes, that's a typo. The condition that you have should be an or. If the service is not the payment service or the method is. Yeah, I think this is one of the key contributions. So we should rework it especially for the paper so that it's obvious.
So you said that the manifests can be checked all the way back up. So that means that on the opposite side, I can actually go down and see who's using that information all the way to the end of all the hops.
Mm-hmm. This is basically what we wanted to have. There was some, maybe I can find it again. Here. The goal maybe is the goal here about recursive disclosure is to enable the front-end service developers to know that 2 services down the road, the payment service is going to critically use my data, right?
I'm thinking about it from a different perspective, and that earlier on you talked about GDPR, and I was thinking about right to be forgotten. One of the pain points of right to be forgotten is if we give the data to somebody to look at, then they become a controller.
Yep.
And we very rapidly can lose track of who they are. So I'm curious if this would give us that kind of visibility.
This would give you that kind of visibility as long as everybody's using the system. Right?
You can know who stores the data for sure. You cannot know what they do once the data is stored and whether or not they delete it. With Tahini only, there are some other systems that provide those guarantees. This is only for like running applications. But
in a way, at some point, this payment server is going to talk to like Stripe or PayPal or something like that. Once they do that, that part we can't really help you with. But within the mesh of the services that are using Tahini, we know exactly where the data is going. We know who has it, so it could actually guide the decision. Yeah, that's a.
I work on the mass open cloud. That's why I spend a lot of my day talking to lawyers.
We should talk afterwards. I've also been doing some sort of there's some other projects doing some sort of deletion things.
That would be awesome.
Okay, I think that we're out of time. Thank you a lot for your attention, and thank you for the questions and the discussion at the end. I think this really helps us figure out what parts of the narrative needs improvement and needs to be better described. So thank you very much for your attention.